I'm going to go over 3 different chapters of Wade, real analysis, and ChatGPT. And so we're talking about the chapters 8, 9, and 10. Point-set topology was, I think, discussed in chapter 8. As one of the subjects, there were other things in chapter 8, but everything else I didn't need to ask ChatGPT about. Then arc to the end, convergence was chapter 9, I believe. And then metric spaces was chapter 10. So for chapter 8, I asked ChatGPT what the difference was between an arbitrary and a finite collection of subsets in point set topology. So yeah, it's all about size, and that sort of sets the discussion. And so this is 3 different threads, one for each chapter, even though I could have done them all in one. Then open and closed balls in point set topology. And I'm going to go fairly fast because there's a lot of topics to discuss, but also I just want to quickly show what the answer was, and you can just stop the video, look at the answer, and keep going. I'm not going to read the details just because this is more about posting all of my questions and just showing what the results look like for comparison later as ChatGPT improves, gets better, gets bigger, changes the way it answers questions. So the difference between open and closed balls, of course, is in the boundary. So it includes the closed ball includes the boundary. The open ball does not include the boundary. And this is something that becomes important later on when you do a volume, because for Jordan regions, the Jordan regions are defined by regions for which the volume of the boundary is 0. And I'll just quote in here what it said at the tail end. And open balls and closed balls are used in the rest of the book, and of course in analysis when you look at the point set topology view of analysis. Here I think it messed up, but I asked the question again and I have an empty answer. And then the concept of relatively open and closed sets. Examples, I got a little stuck here, so I had to ask. And so I'll just go through one of them. So number 1, x is a real line, a is the interval 0 to 1. The set A is closed in x, but the subspace y, 0 to 1, if we consider the subspace y equal to the closed interval between 0 and 1, then A is open in y. So A is relatively open in y. Yeah. So this is a little bit of a complex concept to get. So yeah. Difference between relatively open and open with examples. And it goes through similar examples as it went through before. I want to go back to relatively open because I think it merits just taking a look at it. So let's go back to the first one. The real line is x, a is the interval 0, 1, and the set A is closed in x. But then the subspace y, and this is confusing here, because the subspace y is actually equal to A. So A is open in y. And it's a relatively open set in y. I don't really understand that. I'll have to come back to that. If it's correct, then I don't understand it. So I got to come back to this concept. And I'll go through the first one. So x is the real line, y is 0 to 1 closed. Then the open set is in x, and it's the union of open intervals. But if we consider 0, 1 as a subset of y, which it is, it just excludes the endpoints, it's relatively open in y because it is open in y. Okay, that I get. So I'll have to come back to these concepts for sure. Define connectivity. And of course, I've set it up already for it to be discussing topology, point set topology, and that's very important to always. I always ask the first question in a general way so that it sets up the framework for the discussion. So if I ask define connectivity by itself as a first question, it would probably ask me how to connect electrical equipment or something. Yeah, cannot be divided into two disjoint, non-empty, open subsets. And it's got to do with continuity of functions. Define limit point. So yeah, it can be approached by a sequence of points in the set. And again, I really need to sit down with all these concepts and put them all together. You know, limit point, accumulation point. Yeah. Example of a limit point, set A is 1 over n, and 0 is the limit point. Yeah. And you can use epsilon notation to get to it. When does a set not contain at least one limit point? Discrete set. So it quotes it. Define a compact set. Of course, it's bounded and closed. And I'm setting it up for the Heine-Borel Theorem. I call it Heine. Some people call it Heine. I call it Heine. Examples of compact sets. Of course, any closed set is that is bounded is a compact set, and it does quote the Heine-Borel Theorem. It also goes to higher analysis with Arzela, Ascoli, and number 5, which I have not studied, but I know it's part of measure theory and integration books. It's found in functional analysis books. Then the Heine-Borel Theorem, which is really just the definition of compactness in analysis, and topology. Yeah. Compact subsets of Euclidean spaces with examples. Yeah, so closed and bounded. Then examples of covers and subcovers for the closed interval between 0 and 1. And it sets up the 1 over n to 1 minus 1 over n open interval. And they cover 0 to 1, but don't include the endpoints. Yeah, and then a subcover of that could be the one that goes from 0 to 1/2. Yeah. Examples of why there are no covers or subcovers of 0 to 1 open. Goes into a detailed example. More material that I'll have to revisit in my study of analysis for sure. And it goes back to, again, to the use in item 2 of 1 over the interval from 1 over n to 1 minus 1 over n open. Yeah. Relationship between compactness and connectivity, or connectedness, I should say. It's the way that it's correct. Yeah, so if a compact set is connected, then it must either be right here, a single point or an interval. Okay, I think we're done with point set topology. Let's move on to R to the n convergence. So I asked it to define a separable set. I should have asked a more general questions to get it set up in hindsight, but it did do the right thing by saying in mathematics. Union of two subsets, one dense and countable, and the other consisting of a complement of the dense set. And then I asked for examples of separable set in rationals. And I really like that it's beginning to use some, I guess it's markup, some type of markup language. I'm not sure. It must not be LaTeX because all the other answers that have equations in them are in raw LaTeX and not in markup. But I look forward to the day when ChatGPT will output more LaTeX and a lot of markup. So I mentioned algebraic numbers in this definition, and yeah, that's. I would have asked more, but I got what I needed, so I kept going. I was only asking for an example. And then I asked it to define algebraic numbers. I already knew what they were from Gaussian integers back in number theory, but it gave me some examples that were not imaginary. Well, the roots of these polynomials are imaginary, and they're the algebraic numbers. Never mind. Not all complex numbers are algebraic. Of course, pi. Good example, because it's a transcendental number. A non-degenerate interval cannot have measure 0 with examples. It contains more than one point. And so if it contains more than one point, there's a difference between those points. There has to be some length between those 2 points, at least 2 points. And then it gives you examples, the interval 0, 1 closed being a favor of 1. And it measures the best measure, which I haven't gone into in the book, but I'm sure there'll be a round of that. I'm sure there'll be a round of a lot of the best stuff coming up as I wind down the latter parts of Wade. Example of a closed interval on the real line with measure 0. There is none. Yeah. Example of a Riemann integrable function with countably many points of discontinuity. I mean, it's basically setting up a Lebesgue integrable function, because that's the difference between Riemann and Lebesgue, is that Lebesgue allows countable many points of discontinuity. It mentions that Dirichlet function. Define the closed graph theorem in analysis. This is a theorem that is mentioned in Wade, and so I wanted to ask how I would describe it. And it mentioned linear operators, of course, which I know are very important to a higher level analysis, and I'm looking forward to studying them. Formally, I'm sure, I mean, when you look at examples, there are operators that we are all familiar with from differentiation. Yeah, so to be revisited. Examples of limits of sequence points in R to the n. And here it goes into a bunch of raw LaTeX, which is very difficult to read. This happens in some of the answers. And I'm looking forward to when that doesn't happen in the future. And I'm sure somebody at OpenAI will figure that out. Yeah, so I'd have to go through all of these examples and just write them all out. And I'm sure I did in my notes somewhere. Again, a wall of raw LaTeX, not very readable. Is the empty set a compact set? The answer is no. But it is both open and closed. I know that. So let's go to the last chapter, metric spaces. Definition of a directed line segment in R to the n. Yeah, a part of a line that connects two distinct points. Definition of a hyperplane in vector analysis. Just a plane in R to the n. And in two-dimensional space, it's a line. In three-dimensional space, it's a flat plane. And they're using machine learning and computer vision. Nice. Define a affine subspace. Translates a linear subspace by a fixed vector. So it preserves length. I think it's the way to think about it, in my opinion. Closed under addition and scalar multiplication. Used in geometry. Define subspace codimension. The difference between the dimension of the vector space V and the dimension of the subspace W. I'll have to come back to this when I do linear algebra in more detail. Yeah, this is deep geometry topology used in linear algebra. To be revisited. Then linear operator. Function between two vector spaces that preserves the linear structure of the spaces. Additivity, homogeneity. To be revisited for sure. Examples of linear operators. Scaling, zero, identity, projection, differentiation, of course, one that we're all familiar with, integration, matrix multiplication. Yeah, a readable response to sure. I don't really remember why I asked this question, define topology. I should have asked for define a topology, but it still gave me a definition of topology. It must have fit something that I was reading in weight at the time. Difference between the norms, Euclidean norm, L1 norm, subnorm. They're used a lot in metric spaces. Of course, L1 norm gives you the largest number for the same points when compared to Euclidean and subnorm. And there's always a diagram where you take it's got a square that, yeah, I don't know how to describe it, but it's how you go from 1 to infinity in norms. Sets both open and closed in R to the n. The set of all integers is neither open nor closed. Yeah. Define the discrete space R. Very interesting one. But I asked the question in the wrong way. And yet it did answer it correctly, the discrete topology. I should have asked about the discrete topology instead of the discrete space, where every point is an isolated point. Set of real numbers equipped with discrete topology. A better question, I guess. that goes through it. Chaotic topology. Examples of spaces that are not metric spaces. You cannot measure distances. Not Hausdorff. Yeah, not countable, not separable, not locally Euclidean. Good stuff to come back to when I study more of these concepts. Difference between open and closed sets to describe convergence of sequences in an arbitrary metric space. I'm sure I was reading something when I asked this very long question. And it's all about convergence. Yeah. Openness of a set allows for greater flexibility in terms of the proximity of the sequence to the limit point, while the closedness of a set requires a stronger condition of the sequence being arbitrarily close to the limit point. Define cluster point with examples. It's got infinitely many points near it. That's really the basic fact, I think. Goes through metric spaces for complex numbers, closed interval 0 to 1, closed, standard Euclidean metric. Is every point in a metric space either an isolated point or a cluster point? The answer is yes. And I think this is the last question.